everyone. Thank you for coming to another Climate Matters press conference. I'm the Executive Director of the United Planet Faith and Science Initiative. My name's Stuart Scott, and I'm the host of these programs. And we're coming to you live from Bonn, Germany, COP23. I like to give my email address at the beginning and end of each show so that people can write me afterwards with any questions or comments. Now, today's guests with me are three: Dr. James Hansen, former director of NASA's Goddard Institute for Space Studies, currently the director of Climate Science, Awareness and Solutions Program at Columbia University's Earth Institute, and Pam Pearson, founder and director of the International Cryosphere Climate Initiative. On my right, Dr. Philip Duffy, who's the president and executive director of the Woods Hole Research Center in Massachusetts. He's also former senior advisor to the White House Office of Science and Technology Policy. Today's show we're calling Scientific Reticence, a Threat to Humanity and Nature. Dr. Hansen, would you start us off?
Yeah, that title, I think, is directed to my fellow scientists and also to the negotiators at this climate conference and to the public. Richard Feynman, who I would say is the second greatest physicist of the 20th century, liked to poke fun at his fellow physicists about, I'm not sure he used the word reticence, but there was this famous Millikan's oil drop experiment, which was designed to measure the electron charge. And it got an answer which we now know was not quite right, because he didn't have the right viscosity of air in the calculation. But his fellow scientists, as they did their experiments and were getting a different answer than Millikan, just moved the value a little bit away from Millikan's, and then they would move it a little further and a little further. And after enough years, they finally got to the right answer. But there was a reticence to challenge the expert number. I used this as an example in 2005 and 2007, when I heard from glaciologists, they were beginning to get really worried about the stability of the ice sheets and the threat that they posed to sea level. And yet, you didn't hear that in public. And the IPCC documents had little, if any, contribution from the ice sheets. So I wrote an article about that. But the problem is we don't have decades to come to the right answer. We need to understand that. So, we now know that the temperature rise of the past few decades has raised global temperature far above the prior level in the Holocene, the last 11,000 years during which civilization developed. And in fact, the temperature now is comparable to the maximum temperature in the Eemian, 120,000 years ago, when sea level was 6 to 9 meters higher. Now, the temperature over the last 50 years has been rising almost linearly, and that's brought us to this high level, well above prior Holocene temperatures. Why has it increased almost linearly? The planet is out of energy balance. There's more energy coming in than going out as heat radiation. Because the increasing greenhouse gases are like a blanket, they reduce the heat radiation to space. And the warming would then bring the planet back to energy balance, except we keep adding more gases to the atmosphere at a rate indicated on this chart of about 0.04 watts per meter squared per year. And that has been more or less constant for the last several decades. Now, IPCC has added to their scenarios RCP 2.6, which is designed to keep global warming below 1.5 degrees Celsius. And based on what I showed you already about how warm the planet has already become relative to the Eemian, we really need at most to have global warming of 1.5 degrees. But what's happening is this has no relation to reality. The reality is that climate forcings are not only continuing to increase, but even increase faster. So there's a gap already between the real world and the 1.5 degree scenario. Well, we could do something about that gap. We could say, okay, let's suck some CO2 out of the atmosphere. Well, with the estimated costs of $150 to $350 per ton, at the low end of that range, you're talking about $600 billion to remove the excess of just 1 year's emissions. Or if it's $350 a ton, it's $1.4 trillion. Now you can compare that, just if you don't know what $1 trillion is, the global military budget is 2015 was 1.7 trillion. The United States military budget is $600 billion. We're not going to spend $1 trillion every year to suck CO2 out of the atmosphere. So what we're doing instead is handing young people a situation that's beginning to run out of control. And we have to recognize, scientists are trained to understand, to analyze complex problems. And as we look at this problem, we need to look at the whole picture and make sure that the negotiators and the public understand the situation. The Kyoto Protocol in 1997 was intended to reduce emissions, but you see that even the developed world, the mature economies, all that happened is their emissions have flattened out. And that happened already by 1980, they had flattened out. Kyoto Protocol, where you have each country has a goal, 195 different goals, simply is not effective. And you can see what's happening in the real world. This 1.5 degree scenario requires that emissions be decreased rapidly. It's the equivalent of 3% per year decrease in emissions, plus extracting some CO2 from the air with improved agricultural and forestry practices. And this is simply not happening. The fundamental thing is, and on our recent papers, I have economists as co-authors. It's well understood that as long as fossil fuels remain cheap, we're not going to phase them out. And each country saying, well, we'll try to do better. And we'll maybe increase our targets next year or next decade or 2 decades downstream. That simply has no effect. We've proven that with the Kyoto Protocol. What you have to do is make the price of fossil fuels include their cost to society. That includes air pollution, water pollution, climate change. And if you do that, then we can move to alternatives like renewable energies, energy efficiency, nuclear power. Let everything compete. But as long as we don't make fossil fuels pay their cost to society, we're not going to solve the problem. And so we can't pretend that we're doing that. And we can see this. The scientists should be standing up, in my opinion, and telling the public and telling negotiators, you have to do something that actually has an impact.
So the reticence is really that scientists are not going out of there strictly informational, and they're not telling what their gut feel is?
I think that's right, that the scientists who have looked at this whole problem have got to look at the data. I mean, what science is a case of looking at data and explaining the data. Your theories have to fit the data. And the theory that you can solve this problem without a rising price on carbon has no foundation whatever.
Yeah. I know another climate scientist, a glaciologist, I think, Jason Box, tweeted a naughty word when he heard about methane release in the Laptev Sea, and came under a lot of storm. And of course, if scientists get emotional about what they see going on, then they're subjected to criticism. Is that part of the reason for their reticence to come out with the...
That's a good transition to our next speaker. She's going to address the kind of things that Jason Box was so
Pam?
concerned about.
And this is just a little bit of a preview of a side event where we're looking what we call through a cryosphere lens. And I actually am an ex or perhaps recovering diplomat. I was involved in the Kyoto talks under Clinton, so spent 20 years at the U.S. State Department. And I get how hard this is. But at the same time, increasingly over the past 5 to 10 years, cryosphere scientists have been trying to sound the alarm and trying to get through some of that reticence that Dr. Hansen was talking about. Really, for climate policy goals, the cryosphere has been called a canary in a coal mine, but it is becoming a driver of climate very, very rapidly. And in many ways, an irreversible driver of climate. The thresholds in the cryosphere, snow and ice regions, they are determined not by where we end up, but by peak temperatures in a lot of cases. And the length of time you spend at that peak. Regional and seasonal temperatures, for example, the Arctic, although we're looking at, say, a global mean temperature of 2 degrees, in the summer, the Arctic is projected to be at about 9 degrees, and in the winter months, 12 degrees C over current temperatures.
And 12 C equates to what, about 20 C?
Exactly.
20 Fahrenheit.
Yeah, Fahrenheit. So in other words, the winter temperatures are rising higher than the summer temperatures, which are rising much higher than global mean temperature.
I remember it was raining in the Arctic on New Year's Day a couple of years ago.
Yeah. It's going very, very quickly there. And at times, unfortunately, when the cold air is down over the middle latitudes, giving a false sense that, things maybe aren't that bad, when it's actually that the heat is being displaced, in a sense, up to the Arctic. So overshoot scenarios, as are being discussed, hold much greater risk. And the other issue is that 2100 is, in many ways, a very misleading goal. A lot of the data that you see stops in 2100, but for sea level rise in particular, that is just the beginning. And the worst is that it is locked in. And the current NDCs allow way too many thresholds to be crossed. This is a busy slide. I'm not going to spend much time on it, but basically what the bright red shows is where the Paris NDCs will get us in 2100, but the less shaded red shows where it will get us in 2300. You can't just stop at 2100. There's enough heat and energy built into the system that under the current way that commitments are structured, temperatures are going to continue to increase. The blue lines represent different cryospheric thresholds. I think that those are conservative. This was produced by a consensus group of 36 scientists. About half of them are IPCC scientists working on either the oceans and cryosphere or the 1.5 degree reports. And it was out of date even when it came out in 2015 because the one arrow showing the temperature today was at 0.8 and now we're at 1.1. And this is just 2 years later.
It's interesting to me that you're knocking down that straw man of the date 2100, the year 2100, by going beyond it. But I, in my presentations about climate, go the other way and say we're lulled into a sense of complacency by the fact that all of the data we're told is, by 2100, sea level may be. And so people say, I won't worry about it till 2099.
Exactly. And the problem is that, again, sea level rise in particular is locked in. We will see, if we could halt temperatures today, we're probably looking at between 2 and 3 meters of sea level rise from mountain glaciers, from ocean expansion, thermal expansion, and also from melting that has already started on Greenland and the West Antarctic ice sheet. What really keeps cryosphere scientists up at night, however, are irreversible thresholds, particularly the West Antarctic ice sheet and Greenland. The consensus figure for irreversible melt of Greenland is at 1.6 degrees. And if we remain above that for more than a few centuries, the altitude of Greenland will be lowered to an extent that it will continue to melt irreversibly. It will take thousands of years to happen, but we won't be able to stop it unless we in essence, induce a new ice age. In other words, go down to temperatures below 0 degrees, below pre-industrial. And that is a message, unfortunately, that is not getting out there, even though it's a fairly consensus figure that has been out since really 2012, and nobody has found a better figure than that 1.6.
But it's also, I find it a confusing message, because what you said was if we stay at 1.6 for longer than a few centuries, and again, that will lull people into a sense of complacency. So the question of thresholds, of tipping points, is one that concerns me greatly. And when we get to 1.6, is there a chance that we're going to step back?
And this gets into Dr. Hansen's presentation. It would depend on removal of carbon from the atmosphere that we honestly don't really know how to do effectively.
And it'll cost trillions of dollars.
Yeah, and well, if we can even do it.
So,
it's in RCP 2.6, but it was simply thrown in there as something that we were hoping technology could do without any clear way towards that.
I'm not trying to say that we're locked into doom. I'm just trying to get the scientists to say, oh my God, in public, more, to get out of their measured tones. We're just presenting data, and do as Dr. Hansen and some of the scientists are doing, Dr. Mann, and saying, oh my God, we can't do this. Thank you.
Yeah.
And we'll go to Philip, our third guest.
So I'm going to say, oh my God.
Thank you.
And the subject I'm going to talk about, I think, is certainly very important, arguably the best example of scientific reticence and the consequences of scientific reticence. And what I'm talking about is permafrost, and specifically greenhouse gas emissions from thawing permafrost. And this is a case where I think the natural conservatism of the scientific community, which in many ways is a good thing and a healthy thing, has in this case seriously failed to meet the needs of climate policymakers, and therefore seriously failed to meet the needs of humanity as a whole. So let me just give you a little background on the problem. What is permafrost? Permafrost is ground that's been frozen for a long time. The name suggests permanently frozen, if only it were. 24% of the Northern Hemisphere land area is permafrost. We think that in that permafrost there is about 1,500 gigatons of carbon, and for context, that's about twice what's in the atmosphere now. So it's a truly enormous amount of carbon. And what's happening is, as the Arctic warms, and I think you all know the Arctic is warming at least twice as fast as the rest of the planet, this previously frozen matter is starting to decay, and as it starts to decay and decompose, it emits greenhouse gases, CO2 and methane, into the atmosphere. What this is, it's what we call a climate feedback. It's a self-reinforcing loop whereby warming induces more greenhouse gas emissions. It's absolutely essential that this feedback loop not get going strongly. If it does, there's simply no way to control it. So where does the scientific failure come in? The scientific failure comes in because none of this is in climate models, and none of this is considered in climate policy discussions. Now, that may seem crazy, and it is crazy, and here's where I say, oh my God. But the reason is simply the natural conservatism of scientists, which, as I say, in many ways is a very, very healthy thing. Scientists don't like to be wrong. It's bad for the progress of science if you put forward ideas that are wrong. And so as a result, climate models simply omit greenhouse gas emissions from thawing permafrost. But we know that's the wrong answer, because that then tacitly assumes that these emissions are zero, and we know that that's not right. So this is a huge and underappreciated threat. And what it does is I think mostly underscores what we know already. It underscores the urgency and the need to increase ambition in doing the things that we already know we need to do, which is to stop emitting greenhouse gases by burning fossil fuels and to start removing CO2 from the atmosphere.
I want to ask any or all of you, how do we How do we get there from here, the there being to get more scientists to be more publicly alarmed, to give policymakers a counter sense to the complacency that the IPCC report tends to generate?
Well, I think scientists are beginning to flap their arms and get excited. But what we also have to do is look at the whole problem, because I think the negotiators now realize there is a problem. But what they don't seem to realize is that they're not proposing solutions that will effectively deal with it. And as scientists, when we look at this big picture, we can see that, I think. And we went by the Kyoto Protocol as if, okay, we did something. Well, you look at the data, it didn't do anything. Basically, humanity needs energy. And the countries are going to do what's best for the well-being, economic well-being of their people. And they're going to burn the fuels that are available and which are the cheapest fuels. And that's what we have to look at. It's cheapest this day if we ignore the long-term consequences. So we've got to get those long-term consequences in there in the price of the fossil fuels. It's not there. If your child gets asthma from air pollution, fossil fuel company doesn't pay for it. You pay for it out of your own pocket. The climate damage, not paid for by fossil fuel companies, the taxpayers, or you, if you own a house on the beach. So that's the big problem, which is clear enough, but yet somehow does not seem to be impacting the policy decisions.
We have 3 minutes left. I think we have time perhaps for one question from the audience. I don't want to go too close to the end.
Yes, I would like to ask you, the last presenter, do you have a method to measure emissions from permafrost?
Woods Hole Research Center is one of the things we do. And yes, we do that. It's difficult because we use basically in situ measurements. And the problem is the Arctic is a vast and inaccessible place. The emissions are very, very heterogeneous. They're also different in summer versus winter. And it's particularly difficult to work in the Arctic in winter. So what we're working on is making in situ measurements and also trying to use models and remote sensing to integrate the emissions across the vast territory of the Arctic.
So thank you very much for coming to another Climate Matters show. My name is Stuart Scott. Here's my email address, as I said. You can come and get my card afterwards if you don't have time to take a photo. And I'd ask you one thing as an action item to please go to this very simple website, np4sd.org. It's a Nobel Peace Prize proposal that I've come up with and I'm proposing, which might change the paradigm if the committee decided to implement it. Thank you very, very much.